So it's my pleasure to introduce Matt Dolan to deliver tonight's lecture. Matt did his honours degree at Trinity College in Dublin before moving to Cambridge University, where he completed his PhD in 2010, studying the phenomenology of supersymmetry breaking. He was subsequently a research associate at the University of Durham and Stanford University before joining the faculty here in 2015. He's an internationally renowned expert in the fields of collider physics and also cosmological constraints of dark matter. He's been the recipient of a number of prizes, including the Smith-Rayleigh Knight Essay Prize from the University of Cambridge. Tonight, he's going to speak to us regarding the legacy of Stephen Hawking and the prospects of the Great Reconciliation. Please join me in welcoming Matt.
Lights. Awesome. Thanks very much, Stuart. Can you hear me? Good. So yeah, thanks, Stuart, for the lovely introduction, and thank you all as well for deciding to spend your Friday evening to come and listen to me talk about physics. That's awesome. So I want to spend the next 45 or 50 minutes talking to you about the scientific legacy of Stephen Hawking. So Hawking is, of course, an extremely famous scientist. If you went and you sort of out in the street and grabbed someone by the shoulders and said, "Name me a scientist," you'd probably get Einstein first, and then I think maybe Hawking next. And so what I want to do this evening is give you some idea why we physicists think Hawking was such a great guy beyond his sort of what he's known for more publicly. So, I mean, I'm going to focus on the scientific aspect, but of course, Hawking has a really strong personal legacy for a lot of people, right? So most physicists, when they go out for a walk on the street, do not require police escorts, for instance, right? Most physicists, when we die, we will not have enormous public funerals where both sides of the street are lined with thousands of people. Hawking inspired millions, both through his writings, but also just through his endurance and fortitude in the face of terrible odds. But he was not just sort of a scientific symbol. He was also a person, right? He had a family. This is his wife, Jane. He had 3 kids in the 1970s. So I think it's important that we remember that he was also a normal person who had to deal with everything that we had to deal with, plus a whole lot more. And so he was, I don't know, a very generous person, I think, to a lot of his contemporaries and students, but could also be quite difficult. He was very, very bright, and he knew he was very bright and could be borderline arrogant sometimes. And so his friend and collaborator, Roger Penrose, wrote a really beautiful obituary in The Guardian when he passed away, which explores a lot of those aspects of his personality. So like a lot of people, when I was a teenager, I got The Brief History of Time out from my local library in Ireland. And I thought, wow, that's amazing. I don't understand any of it. And so then I went to university in Dublin, as Stuart was saying. And when I was an undergraduate there, Hawking visited Dublin and he gave a lecture, not a public lecture like this, but a proper scientific lecture about what he thought was the solution of one of the problems I'll talk about in this lecture. And I went to that and I thought, wow, that was amazing. I didn't understand any of it. But after that, I thought, well, I really want to do physics. And I think Cambridge, like after this, surely Cambridge is the place to go to do physics. So I went to Cambridge. This is the Department of Applied Maths and Theoretical Physics. Everyone in this building is working on cosmology or particle physics or general relativity. I could only find a picture of it being built about 15 years ago. So my office was here, and this was Hawking's office here. And it was all open plan on the inside, so whenever he'd come in, you could hear him sort of beeping his way up the elevator and beeping around upstairs, which was awesome. It was really amazing and inspiring to be able to have him as a colleague. He was, of course, very famous. I haven't worked anywhere else where we've had to negotiate so many television crews. But he was also very much a part of the department and the departmental culture. He'd come to seminars. In fact, there was a seminar every Friday on relativity that he worked on. And there was always lunch provided at the seminar because he paid for it all. So it was really great to be able to interact with him a bit. And louder? OK. I will speak louder. And so it was really amazing. The mic is maxed out already, apparently. So it was amazing to be able to interact with him. And so I was really sort of deeply saddened when I heard that he passed away in March. But then David Jameson, who gave last week's lecture, asked me to give this talk. And I thought, well, what a fantastic opportunity for me to reflect upon what his scientific contributions were. So, of course, he didn't only have personal contributions. He was sort of a major cultural figure. He had beer with Homer Simpson in the 90s. He also played, so in Star Trek, he played, this is Data, this is Einstein and Newton at poker on the holodeck. He beat Einstein. Einstein thought he was bluffing, but he didn't bluff. Newton wisely folded. And he was portrayed not only by Eddie Redmayne, but also by Benedict Cumberbatch. So this tells me that anybody can play Stephen Hawking if you have the right haircut and glasses. So this is in Theory of Everything with Eddie Redmayne. This is David Thewlis. So this is meant to be Hawking's supervisor, Dennis Sciama. So we'll come back to him a couple of times in this lecture. And this is Benedict Cumberbatch. This one is less well known. This is a BBC TV movie made in 2004. So this is before he had become the great Benedict Cumberbatch that we all know and love today. So the main reason why he's famous culturally is because of this book, right? Brief History of Time. So who here has read Brief History of Time? Yeah. Who here, I mean, most of you have probably not read any other physics book, or maybe not for this crowd. But this is the biggie, right? This sort of starts it all off. So this was published in 1988. And he'd wanted since the early 80s to write a physics book. He'd sort of started and drafted and got distracted by other things, partly to explain cosmology to everyone and what his ideas on the universe were. But he was a father of 3 kids. He had an ongoing medical condition. So there was also some school fees that had to be paid. So this is also part of his motivation for writing Brief History. And it just went gangbusters. So it's sold more than 10 million copies. Some of them were even read and been translated into like 40 languages. And he kept writing books through his career. So Black Holes and Baby Universes. This is quite nice. This is a collection of essays with some more sort of personal reflections about him growing up and that kind of stuff. Universe in a Nutshell, a briefer history of time. I mean, this is not already a very long book. I don't know why this was necessary. And a book called The Grand Design most recently. So 50 years of July lectures is kind of our theme, and that's actually not a bad place to start in a lecture about Stephen Hawking, because that's sort of just about where he was getting going. So 50 years ago, students were busy rioting in Paris, of course. This is, I mean, David used John Gorton last week. This is McEwen. So he was prime minister for 23 days after Holt disappeared. So, and then there was an election and Gorton got put in, and then he became the first deputy prime minister, apparently. So in 1968, this was your computer. This was a whiz-bang thing to have in 1968, apparently. This is an early HP machine. And they didn't call it a computer, they called it a personal calculator. They thought if they called it a computer, no one would believe them, because everyone knew computers had to be much bigger than that. And this thing didn't fill a room, so it couldn't be a proper computer. But it would set you back $5,000 for this calculator. The Rolling Stones had released Beggars Banquet, Electric Ladyland, the White Album, which is the background. I guess everyone's listening to Easy Beats over here. And Stephen Hawking and Jane Wilde had just sort of settled in to a new house in Cambridge soon after Hawking had finished his PhD. So he was just getting going in his scientific career 50 years ago when Tony Klein and everyone was attending the first lectures here. So I'll just bring us quickly up to speed, up to 1968, and then we'll start talking about the science. So he was born in 1942 in Oxford. His parents bought a house in London during the war. You could buy a house pretty cheap in London during the war. So a V-2 rocket landed down the street from his house after they moved there. So he does sort of straddle eras. When he was 17, he went off to Oxford to study physics and chemistry. So when he was at Oxford, he had a pretty good social life. He joined the boat club. This is the college boat club. This is Stephen Hawking with the handkerchief. And then he graduated from Oxford 3 years later, and went off to Cambridge. So the story is, I mean, he told it, it's probably a true story. So he was on the borderline between getting first-class honors and second-class honors. And so he had an interview to decide which way would it go for him. And he said, well, look, if you give me first-class honors, I'll go to Cambridge. But if you give me a 2-1, I'm going to stay here in Oxford. So they gave him first-class honors and got rid of him. So he went off to Cambridge and started a PhD with this guy, Sciama. And then midway through his PhD, he got diagnosed with ALS, or motor neuron disease, a highly traumatic incident, which I think is pretty well portrayed in Theory of Everything. But married the year after Jane Wilde, who we saw in the picture before, right? So then he managed to finish his PhD in '66 and started a research fellowship, so a a follow-on position where you just do research and try and write physics papers at one of the Cambridge colleges. So I want to pick things up around there. So Hawking was really, I mean, he was very brilliant, but he was also somewhat lucky in a sense. He arrived at Cambridge rather than Oxford, just at the right time in some sense. So 1960 to 75 is something that is now called the golden age of general relativity. Right? It's a period where massive progress was made on this theory, I don't know, to an extent which hadn't been previously before. Right? So, and he continued working in this area of relativity for basically the rest of his career in various aspects. And so what is this general relativity? So general relativity is a theory of gravity. So the full title is the general theory of relativity, but we just usually call it general relativity. And it was invented in Einstein and other people to explain various features of gravity. So there's an original theory of gravity, and that goes all the way back to Sir Isaac Newton in the 1680s in his great book Principia Mathematica. So Newton's theory of gravity is pretty simple. We can cover it in a slide, basically. Consider two objects. We're going to hold them a distance d apart. Take that and square it. So if they're 2 meters apart, now you've got 4. Take 1 over that, so now you've got a quarter. And Newton says the gravitational force is proportional to that. So you take that quarter, multiply the masses together, and multiply it by a special constant, the gravitational constant, which is determining a characteristic feature of gravity. So that's it. That's Newton's theory of gravity, well, in a nutshell, a brief history of Newton's theory of gravity. Okay, so you have two things, and you just multiply it all together, divide by the distance squared. Of course, the brilliance in this of what Newton did was it's very not obvious from those words I just said that that leads to things like planets orbiting around the sun or the tides. And Newton showed that. That was his great achievement. So fast forward then 200 years, and we get to Einstein. So in 1905, Einstein came up with a theory called the special theory of relativity. And one of the hypotheses that went into this is that there's a cosmic speed limit. There's a speed in the universe, and you can't go faster than that. And that speed is the speed of light. In physics, we usually abbreviate it just to c. So the Latin for speed is celeritas. And it's pretty fast. It's about 1 billion kilometers per hour, or 300 million meters per second. Now, Newton's theory, which I talked about in the previous page, it doesn't have this speed limit. According to Newton, force acts instantaneously, and you can go as fast as you like. So there was an obvious problem here of how do you make Einstein's theory of special relativity, which we knew to be correct from experiments, and Newton's theory of gravity, which we knew to be pretty good from experiments, consistent with one another. And this was the problem which occupied Einstein for the next decade of his life. So before we get to general rel, the fact that we now have a cosmic speed limit in the universe has some pretty important implications. So we can't go faster than the speed of light now. Well, we never could, but now we know we can't. So if you want to escape the gravity of something, there's a minimum speed you have to go at. That's called the escape velocity. Right, so if I probably shouldn't throw this up. I should throw something else up. If I throw up my bottle of water, it'll come back down, right? If I throw it up faster, it goes higher. And eventually, if I could throw my bottle of water fast enough, it would escape the Earth's gravity entirely and simply never come back. Now, there's a minimum speed I have to throw it up to do that, and that's called the escape velocity. So for the Earth, it's 11 kilometers per second. That's about 40,000 kilometers per hour. And then it's smaller for the Moon, because the Moon is smaller. And for the Milky Way, it's pretty big. But what if an object had an escape velocity that was larger than the speed of light? Well, the speed of light is now your speed limit. You can't go faster. So you can never escape from that object. These objects are called black holes, right? And they're actually hypothesized back in 1784 originally. So before Einstein, someone noticed that, well, you could have a strong enough gravitational force that light wouldn't escape. We're going to come back to these again and again. They'll be a central feature of this lecture. So Einstein beavered away for 10 years with the help of some of the best mathematicians of the time and come up with a theory, a successful theory, called the general theory of relativity. And so this worked really well. Sort of straight away, it was able to resolve some features of, for instance, the orbit of Mercury, which simply couldn't be explained by Newton. So people latched on pretty way that this was a good thing. So general relativity is notoriously difficult. We don't teach it to our undergraduates at all, really. You have to sort of do your 3 years of physics and maths, then get to a graduate degree, and then you probably know enough that we can start to teach you general relativity. However, the vague picture is that you can imagine space-time is something like a rubber sheet. Earth or a planet sits in that, deforms the rubber sheet, and then the moon will sort of circle around on that rubber sheet. Now this is, I have mixed feelings about this. It's an analogy. You know, if I had Earth on the rubber sheet, what's pulling it down? Well, gravity, which is already there because we're on the Earth. So this only works so far, but it gives you an idea. A better picture is kind of this animation. So just the fact that this object exists in here, it has mass, so by E equals mc squared, it has some energy, and Einstein's equations tell you that energy deforms space-time. So it deforms not only the space around the object, but there's little clocks running here. It also deforms how time runs. So John Wheeler, who is an American theoretical physicist, sort of summed this up in a pithy sentence: space-time tells matter how to move, matter tells space-time how to curve. So there's going to be quite a few analogies in this talk. And I mean, even part of it is Hawking trying to figure out if something is an analogy or not. So we have to be careful of these, right? So XKCD summed this up pretty well. Space-time is like a rubber sheet. Objects distort the sheet, but what's pulling it down? Well, really, space-time is like this set of equations, and any analogy is an approximation to the set of equations, okay? So if you're flying with an analogy and it stops making sense, it is still an analogy. If I stop making sense, it's probably my fault. So I've only got two equations in this. So one is this next one. So apparently when Hawking first sent off his draft to his publisher, it was full of equations, and the publisher said there's no way, absolutely no way. For any equation you put in, you lose half your readership. So he only ended up with one equation in there, which was E equals mc squared. I've got two equations, but you're all here already. I can see you. So if half of you leave, I'll be quite put out. So this is the equation that Einstein came up with. It's called the Einstein field equations. It's sort of one equation which is standing in for a whole lot of other ones. R mu nu minus a half R g mu nu equals 8 pi g over c to the 4 times t mu nu. That doesn't mean very much. But on the left, the basic idea is on the left-hand side here, you got some equations which are determining the geometry of space-time. So this guy G here, it's a mathematical object which is telling you in space-time what is the distance between two objects, basically. And these R's are made out of these G's. And on the right-hand side here, well, we see this G. This G is the gravitational constant before, so we know our theory is dealing with gravity. This C is the speed of light. That tells me that it's relativistic. Whenever I see G's and C's together, I know I'm dealing with something that has relativity and gravity. And this guy T over here is some character which tells you about where is the energy and matter in the universe. So the energy and matter over here is affecting the distance between stuff over here, and the fact that you have some distance and space-time equations over here is affecting what the matter is doing. And because these equations sort of bounce off each other like that, it makes them very difficult to solve. In fact, when Einstein wrote them down, he could really just sort of approximate what the solutions might be like, or what certain solutions might be like. And he sort of thought in 1915, well, maybe these are really hard. Maybe nobody will ever solve these equations or come up with a solution for them. And then in 1916, this guy, Schwartz Field, came up with the first exact solution of the Einstein equations, which was really impressive. So at the time Schwartz Field was serving on the Russian front, he volunteered for the German army and went out there and was reading. Einstein's papers were sent out to him, and he was sort of reading them while serving. And he thought, well, I'm going to try and solve these. I mean, he was a physicist. He wasn't just a soldier with a hobby. So he thought, well, the equations are really hard. How could I make them easier? They're for gravity, so I want to solve them for something like a star. Now, if I look at the sun, it's pretty circular. So I'll only look for solutions which have perfect sphericalness. So that makes it easier to solve. And time is tricky, so we'll just say that we're going to look for a solution where nothing is moving. Perfectly static, nothing rotates around at all. And so making those assumptions, Schwartz Field was able to actually solve the Einstein equations exactly. You can go and write down an equation in about a line. I mean, solving it takes longer, but the equation itself for that G is about a line. And this is an amazing achievement. And so he had a solution in general relativity for what gravity does near a star. Now, his solution had an interesting feature. If you went right to the center of it, it had something called a singularity. So at one point in space-time, the gravitational force and the curvature of space-time became infinite. And this caused a lot of people a lot of I don't know, grief over the next 40 years, basically. So from the perspective of a star, this was OK, because basically Schwartz Field's solution described the outside of the star. And if you wanted to describe the inside, you had to use a different solution, right? The inside of the sun and the outside of the sun are very different. And so you use different solutions in general relativity, and you kind of match them onto one another. And so when you're talking about stars, you don't have to worry about this singularity. But you could still think, well, if I think about the whole solution Schwartz Field wrote down, what's going on? I mean, this thing is sort of predicting infinite force, and it doesn't really make sense. And so understanding what this meant, well, it was sort of the next 60 years of general relativity, basically. So this caused a lot of confusion in the 20s and 30s. No one really knew what it was, or what it was doing there. And then finally in the 50s, someone realized that this Schwartz Field solution that he's written down, it's actually the equations for a black hole. This thing I described a few slides ago where light can't escape from something, that's exactly what's going on here. There's sort of a singularity here, and if you're within a certain distance of the singularity, light can never escape. OK, but what is really the meaning of it? This is still a very strange thing that we have these infinities in our theory. It's telling us that things break down. We don't really trust what's going on anymore. And so people had an argument for about 40 years as to this singularity here in the equations. Is this just an artifact of using solutions that are too symmetric? So Schwartz Field had, he'd assumed that it was a static solution, there was no time, and it was perfectly symmetric. And then he found this singularity. Now, obviously, if we look around us in the universe, the sun is pretty symmetric, but it's not perfect. It's this bubbling, boiling mass of fusing hydrogen and helium. So nothing is really that symmetric. And it also has time dependence. So the thought was, well, maybe if we make it a bit more realistic, this will disappear. And so a major question was, do black holes exist? And people sort of were confused by all this, and actually not much happened in relativity for 40 or 50 years after Einstein wrote the equations in 1915. So let's look at the anatomy of a black hole a bit closer, since we'll be talking about them for the next half an hour. So here's the singularity in the middle. You imagine we're just looking down on it somehow. It's in 3 dimensions. So here's the singularity at the middle. And out here in the white space, well, you're far enough away from it that your escape velocity is less than the speed of light. So inside your rocket ship, you could sort of turn it around and fly away, and no problems if you had a sufficiently good rocket ship. As you get closer to the black hole, gravity becomes stronger. The force of gravity is stronger. And eventually, the escape velocity is equal to the speed of light, right? The escape velocity is equal to the speed of light exactly at the rim of this circle, right? So the location where the escape velocity is the speed of light is called the event horizon. It's not a physical location. Nothing is exploding there. If you had a big black hole, you could sail right through the event horizon, probably without realizing it. And terrible things would happen to you later on. But at that moment, you'd be OK. So basically, once you're on the outside here, you're fine. Once you're on the inside, you'll never get out again. Because of the cosmic speed limit, you can't travel faster than the speed of light. So you'll be stuck in here, and you'll fall into the singularity, and you'll be destroyed. Okay. That's not funny. OK, so you can never get out once you're in there. And so there's a characteristic distance, which is named after Schwartz Field. So this event horizon, this is a perfectly spherically symmetric solution. So it looks like a circle here, but really in the full thing, it's the surface of a sphere. The surface of a ball is what it looks like. But you can't see it, obviously. Right? It's not a physical thing in that sense. So I mean, we'll come back with an analogy with a suitable warning. It's kind of like if you had a waterfall or a plug hole, and you had a little boat, and the water gets faster as it goes down. And that's like the force of gravity. So if you're outside the event horizon, well, you can just putt away and escape, and you'll be fine. At some location, you can turn up the boat's engine to maximum, and you will just be staying in place, right? That's like at the event horizon, you could travel at the speed of light, and you could stay there. But once you go inside, your boat's going to get pulled down the drain because you can't travel faster than the speed of light or the speed of the water going down, and you get, you end up well, down the drain. So this was the big controversy. What's a singularity, and do black holes actually exist, right? They're enough in pop culture now that it's kind of taken for granted. Oh yeah, black holes, well, they're out there. But in the 60s, this was not a given at all. This was a major scientific question of the day. And the view, the sort of consensus view in the scientific community was probably no. Realistic solutions of Einstein's equations that are not perfectly symmetric will not involve singularities, because singularities are disgusting. This was kind of the feeling. And then this character came along. So Roger Penrose came along, and he had a completely new way of thinking about this problem. He used a branch of mathematics called topology, and the physicists hadn't really thought about using this before. So Penrose is, I think he's 5 or 10 years older than Hawking, and they started working together in the late 60s and became lifelong friends. Penrose is also an awesome artist, right? So like, he drew this on the blackboard, and I don't know what this is, but it looks fantastic. But I've been to talks by Penrose, and his talks are beautiful. So he uses the old transparencies, and his transparencies are covered in beautiful diagrams like this, and then he can layer the transparencies on top of one another, so the whole picture just builds up over several transparencies as he talks you through what's going on in all kinds of different colors. Really awesome talks. So what was the old way of thinking about singularities? Well, the old way was basically pick a specific solution of the Einstein equations, like this Schwartz Field solution I described, and study it to death mathematically. And so but there's lots of solutions. You can write down many solutions of the Einstein equations, and as you lose the symmetric sort of properties that Schwartz Field was studying, it becomes harder and harder to solve them and study them. So the new way that Penrose said, sort of physical reasonable solutions should have certain properties, nice properties, and use arguments from this field of topology to show that any solution with these properties will lead to a black hole forming. So rather than study one solution at a time, Penrose said, well, we can kind of study all of them at once. So the question is, what's topology and what kind of properties do these solutions of the Einstein equations have to have in order to get us black holes? Well, this hinges around topology, and topology is now basically everywhere in theoretical physics. It's in particle physics, it's in cosmology, it's in solid state physics. It's pretty hard to escape if you're a theorist now. In the 60s, it was still pretty exotic. Topology is a branch of mathematics which studies the properties of sort of shapes in multiple dimensions under sort of deformations like stretching and bending and that kind of thing. You can't tear things apart, but you can sort of move them around. So to topologists, the classic example is the coffee cup is the same as the donut, right? So if you start with the donut here, you can prod the donut around. You can twist it and bend it a bit. Get to here, it's a bit flat on top. You could stick your thumb in the top then, and then it becomes looking like this, and that's basically your coffee cup. The topologist doesn't really care. I mean, he's missing out on like the delicious donut, obviously, but he doesn't really care about the taste of the donut. He just cares that this thing has a hole and this thing also has a hole. From the perspective of the overall shape, that's what he cares about, or she. So Penrose was a mathematician by trade, and he interacted, and this was his advantage in this. This is sort of a unique selling point. And he interacted with Sharma, so Hawking's supervisor from a few slides ago. And Hawking's supervisor said, you know what, I mean, you should start thinking about this general relativity. It's pretty good. And so Penrose did. So Penrose is famous for a lot of other stuff as well in maths. So this is called a Penrose triangle. It's an impossible triangle. You may have heard of the artist M.C. Escher, so this artist who drew impossible staircases. Penrose knew him, and they interacted. And sort of Penrose inspired a lot of his crazy drawings. So Penrose's conditions are pretty reasonable, actually. He says, well, energy should be positive. That sounds all right to me. In some region of space-time, gravity should be he has more mathematical, but this is basically what they mean. Gravity should be strong, so gravity is an attractive force, so stuff should be really sort of falling inwards quite fast. And we don't allow crazy things to happen like traveling backwards in time. And then he says, if you have these things satisfied, you'll get a singularity. It's a generic feature. When are these kind of conditions satisfied? Well, in certain kinds of collapsing stars, they're satisfied all the time. So this was a real game changer for relativity. It meant you didn't have to study a single solution. You could say vast general theorems. And it also, of course, implied that black holes probably exist in our universe, because stars do collapse. So then Hawking came on the scene. This is Hawking's sort of first big contribution. And he basically ran Penrose's argument backwards. So Penrose says, in a collapsing star, everything is getting closer together, becoming more compact and more dense. And that leads us to this singularity in a black hole. So Hawking came along and said, well, in the early universe, everything is getting further apart and less compact and less dense. So that means it probably came from a singularity rather than going into one. So we call this now the Big Bang, right? So in the 60s, this was again really up for grabs and quite controversial. And Hawking tells us that if we run back the clock on our universe, it ends up in this very hot, dense state earlier on, which is well attested experimentally. And then according to general relativity, there's a singularity at the beginning. Well, what that really means is we don't know what happened at the beginning. If you have this region, this single point of infinite force and curvature, relativity is saying, my equations break down, do not use me anymore. So this is quite a good achievement by Hawking. It means that we don't know what's happening there at the instant of the Big Bang. So soon after this, Hawking wrote a book. So he wrote it with George Ellis, who was another student of Sharma. This book is called The Large-Scale Structure of Spacetime, and it's mega classic in physics. So this is pretty much the definitive book on what are called the singularity theorems, or the Hawking-Penrose singularity theorems. I've got a copy. Lots of people. You'll see this in many offices. It's a characteristic awful orange color. Okay? So I thought, regarding this sort of beginning of space-time of the universe, this is the last sentence of this book, which is quite nice. The actual point of creation, the singularity, is outside the scope of the currently known laws of physics. So you can go back so far with general relativity, but you can't go any further. You need a new theory. Something else has to happen if you're to understand what is happening at the beginning of space-time or at these singularities in general. So this is sort of the first big thing that Hawking did, these singularity theorems. And these still hold, right? These are, I don't know, Hawking basically, I mean, with Penrose, he started, but he basically also finished the subject. They just sort of, they cleaned it up between themselves over this period of 5 years. Hawking wrote a book, and there's not a huge amount more that you can add to that, other than these are awesome. So did this sort of set up that black holes exist? Well, it implied that they do, but do they? Well, we know now the answer is yes, actually. So this is an image from the LIGO, or affiliates of the LIGO collaboration. It's a pair of black holes orbiting together, spiraling in towards one another, and then eventually crashing into one another. So the waves here are showing gravitational waves, and this isn't just an animation. This is what happens if you get an exact solution of the equations of general relativity. You can get two black holes, spin them together on your computer, and solve it and get this. And then you get these, they collide, and you get these gravitational waves coming out. So these equations are so difficult that no one was actually able to do this calculation on their computer before about 2005. So even though relativity is now 100 years old, only basically in the past decade have we figured out computationally how we can actually do that. And that's a critical part of LIGO searching for black holes. So in September 2015, the LIGO experiment observed the gravitational wave signature of colliding black holes. And then 2 years later, Ray Weiss, Barry Barish, and Kip Thorne won the Nobel Prize for this. So Kip Thorne was pals with Hawking back in the 70s, and they made a bet. So the bet was, do black holes exist? Hawking, of course, had just proven some awesome theorems saying that they do. So he bet against black holes existing. And he figured that if he lost the bet, it was all right, because black holes would exist, and he'd be so happy anyway. But if he won the bet, well, at least he would have won the bet. So he bet that they didn't exist. Kip Thorne bet that they did regarding a particular black hole called Cygnus X1. And eventually, so the bet was that if Hawking won, he would get 4 years of Private Eye subscription, the British newspaper. And if Kip Thorne won, he'd get 1 year of Penthouse. So Kip Thorne in the 80s got his year of Penthouse. Hawking conceded that bet. Hawking quite liked making bets. He did it a number of times in his career. So soon after this, so this is we're in about 1970 now. I'm kind of going chronologically between about 1970 and 77, not because chronologically is always the best way, but I don't know, there's a sort of a thread that you can follow through the thinking here between all the discoveries that he's making at this time. So this is now the early 70s. So soon after these singularity theorems had happened, and he proved those, he made an interesting observation. It's a proof. It's a mathematical sort of proof, basically. If you have one of these black holes, and they have an event horizon, it's like I said, it's sort of the area, it's the surface, basically, of a ball in 3 dimensions, so it has an area rather than a volume. And he proved that the area of the event horizon, it will never decrease in general relativity. So you can take a black hole, it's got an event horizon, you can do whatever you like. You can throw a whole bunch of stuff at it, throw some stuff in the black hole. You could leave it there and let it wobble around and evolve in time. You could throw black holes at each other, like on the previous animation. And what Hawking proved was the area won't get smaller of the event horizon. So this is just to him kind of interesting. And then this guy came along. So this is Jacob Bekenstein. Bekenstein at this stage was a PhD student. He was a graduate student at Princeton University with John Wheeler, so the same guy who did the space-time telling matter how to curve story. And Bekenstein said, oh, I know something else that doesn't decrease. Entropy doesn't decrease. This is just like entropy. So what's entropy? And this is also, well, this led to a big argument. But let's go through entropy first. Entropy is basically a way that we have in physics and information theory and computer science of measuring sort of the amount of disorder that there is in a system. So before Bekenstein, no one thought this had anything to do with black holes. No one had even considered that possibility. So Robert Wald is a physicist. He is a renowned expert on general relativity. He literally wrote the book on general relativity. if you've taken a graduate school course on general rel any time in the past 30 years, you have probably used Robert Wald's book on general relativity. And so Wald was a contemporary of Bekenstein, and he thought, and I quote, "I felt this is an utterly ridiculous project to work on." So no one at the time thought this made any sense or was a good idea, except Bekenstein. And Wheeler thought it was so crazy it might be right, which was very much his style. So what's entropy? It counts the number of ways that you can arrange stuff inside a system, basically. So say we had a playroom, tile floor, and 20 toys. So if we stick all the toys in the corner, that's pretty clean. It's pretty tidy. We'd be happy with that as parents. It's quite ordered. So this has a pretty low entropy. It's telling me that the system is quite ordered. Another way you can think about that is how much information do I have to give you for you to know where all the toys are? In this case, I can say it in a sentence, the toys are all in the top left-hand corner, right? So I've told you that, one piece of information, but you know where all 20 of the toys are. So it's pretty straightforward. However, playrooms are not always so tidy. We might have this kind of configuration of our 20 toys on the floor. This is still pretty reasonably tidy. They're at least sort of up against one of the edges. It's less ordered, but still kind of tidy. But there's lots of different ways I could arrange the toys that would still give me this pattern. I could swap the blue ball here and the white ball here. It would look basically the same, but it's a different configuration of the toys. So the fact entropy basically counts the number of ways you can arrange the toys around so that it would still be exactly this pattern, essentially of 3, 1, 1, 5, 0, blah, blah, blah. You can count these if they're restricted into the first row, how old the toys are. There's 10 to the power of 20 ways you can do that, which is a lot. So basically, you can get that. If you just want everything to be in the first row, there's 10 places you could place the first toy. There's 10 places you could place the second toy. So you end up with 10 times 10 times 10, up to the power of 20 ways that you can stick toys in this first row. And the way that we define entropy in physics is take what's called the logarithm of this number. All this means is if I give you something that's 10 to the power of some number, just take the number that's up there, right? So it just says pick the small number above the 10, and we call that the entropy. That's all it means. So the entropy of this configuration is 20. Now we can also go to a maximally disordered state after a tantrum. All the toys are now randomly strewn around the room. It is maximally disordered now in the playroom. So now there's a lot of ways I can configure all the toys around. There's 100 different squares, and each one has a toy. So I'd have 100 times 100 times 100 to the power of 20, which is also equal to 10 to the power of 40, which is an awful lot. And so the entropy here is I just pick out the number at the top, the small number above the 10, so that's 40. The entropy, so the system is highly disordered. So this entropy is a measure of the number of ways a given configuration of a physical system can exist. So usually in physics, we don't talk about toys on floors. And so the reason that entropy is interesting for us and for Bekenstein is there's something called the Second Law of Thermodynamics, right? And that says entropy doesn't decrease. So if you start with a configuration like this, leave either time or a child in the room, you will evolve to a configuration like this, right? And the story is entropy doesn't decrease. This is very low entropy. This is very high entropy. You might, the room will start like this and end like this, but it will very rarely go the other way around in the presence of such a child. So in physics, we're not usually interested in babies in toy rooms, but if you kind of squint at this, this looks a bit like gas in a box. So I can imagine I have a box, and I have gas that just starts up all in this left-hand corner, and then I let time run. As I let time run, the gas is going to diffuse throughout the box, and all the gas molecules sometime later will be in essentially random locations. And this statement of the second law is that we evolve from a ordered to a more disordered state always. Or it doesn't decrease, so it can stay the same, or it will get bigger, basically. So the critical thing here is that this is a system, and it has some bits and pieces, and we can count all the bits and pieces and how it's put together. And so the analogy that Bekenstein drew was, the area of the event horizon never decreases. This is what Hawking proved. And the entropy of the physical system never decreases. And this is amazing. Look what I've done. To be honest, this paper of Bekenstein is totally visionary. It's a beautiful and incredible paper. One of the best papers around. It's really, really amazing. But Hawking said, well, look, that's interesting, but analogy alert, that's just an analogy Bekenstein. And Bekenstein sort of said, no, we have to take it pretty seriously, because I can't really think the second law of thermodynamics, it doesn't get broken. So the area of a black hole really is a manifestation somehow of their entropy. And so Hawking, he wasn't really happy with this. They argued for a couple of years. But Hawking went away and actually managed not just for the second law of thermodynamics, but for all the 4 laws of thermodynamics to come up with sort of black hole analogies. So these are called the laws of black hole thermodynamics. And they work like this. So this is a paper with a guy called Bardeen and an Australian called Carter. So the normal thermodynamics on the left and black hole thermodynamics on the right. So the temperature of a body in equilibrium is constant. Right? If you just leave something there for a long time, it will all be at the same temperature. For black holes, the surface gravity of a black hole is constant. So surface gravity means look at the event horizon, and this theorem, you can prove this mathematically, says the gravitational force on that event horizon, so that sort of surface you can or can't escape from, is always constant. The first law of thermodynamics relates the change in energy, so to the change in entropy or rotation or electromagnetic charge of your system. So if you have some system and you spin it around, its energy will change, and the first law relates these things to one another. For black holes, you could have a black hole, it has some area, it could be spinning, it might have some electromagnetic charge, and the first law of black hole thermodynamics relates the change in energy to these things in a similar way. The second law is what Bekenstein started with. Entropy is a non-decreasing function of time for normal thermodynamics, normal physical systems. And for black holes, the area doesn't decrease. And then finally, in normal thermodynamics, we have a third law. You can't have something that has 0 temperature. So this temperature is measured in what are called Kelvin. So to go from Celsius to Kelvin, you subtract minus 273. And then the analogous law for black holes, you can't have a black hole that has 0 surface gravity. So all this on the left is sort of known since the 19th century for like normal systems of gases and all that kind of stuff. Everything on the right you can prove in maths in general relativity. And this was a paper by Hawking, and it's a really beautiful achievement. So this teaches you, like before this, there wasn't much you could say about black holes, and then suddenly you had these 4 laws that they all had to obey, and it works pretty much in all dimensions for any black hole. But Hawking was bothered by this. He was not happy at all. And the reason he wasn't happy was by the second law. Because in thermodynamics, if you have a normal system, anything that has an entropy has a temperature, but just a normal temperature. And anything that has a temperature radiates energy or heat. But according to the analogies, entropy is like area. So, but if black holes have a entropy, they must also have a temperature. But if a black hole has a temperature, it could also radiate. But then it wouldn't be black. So this really puzzled people. In particular, Hawking was very annoyed by this, this area entropy thing. And so he thought, well, maybe like it's not really black hole thermodynamics, it's an analogy. And the analogy breaks. But he was a good physicist. So instead of sort of just saying, having an argument with Bekenstein and leaving it there, he went away and he did a calculation. And in his calculation, he proved himself wrong. Hawking was very happy to be wrong throughout his career, which is a really good thing in a scientist. So the same Kip Thorne from a few slides ago once said he's like the Evel Knievel of physics. You know, he's willing. Do people even know who Evel Knievel was anymore? Awesome, great. So you know, he was a bit of a daredevil in his conjectures and what he was willing to go out and say, but he was also willing to take a fall. And that's a great sort of feature to have as a physicist, to go out and make some conjectures, you know, and just like, okay, I could be wrong, but let's go and see what happens. So Hawking wrote this paper, and I've just sort of pulled the title. This is actually from the paper. It's called Particle Creation by Black Holes. It's the most famous paper he ever wrote. It has one of the most highly cited papers in all of theoretical physics. So he did the work in 1974, announced it in 74, and the paper came out in 75. So he knew that he wanted to do a calculation with black holes involving radiation, and this hadn't really been done before. And there's a sort of a physical theory we have which sort of tells you about physical processes involving radiation. This is called quantum mechanics. This was developed in the 1920s, and it usually is applied to very small systems like atoms. So here's a helium atom. So a helium atom is, you know, it's got some bunch of electrons around here. There's a small nucleus, and this whole width of the helium atom is about 1 angstrom. So 1 angstrom is 10 to the minus 10 meters. So it's very small. And usually we use quantum mechanics for sort of doing calculations with these things. Black holes are not necessarily very small, and black holes are pretty big. So why does quantum mechanics matter? Well, Hawking sort of said, these effects, these quantum effects could be small, but the universe goes on for a very long time. And so these small effects could add up and be quite important. And so he went, and in this paper, he did a tour de force calculation for the time using quantum mechanics and general relativity put together. And he found that according to quantum theory, black holes could radiate. So once they could radiate, that meant they had a temperature. And this meant that basically Bekenstein from the start had been right. And the black hole thermodynamics laws were not just analogies, but they really were thermodynamics for black holes. So this was pretty amazing. This is now called Hawking radiation, the fact that black holes can emit particles. So this is my second equation, the Hawking radiation equation. So in 1974, just when he was doing this calculation, Hawking got elected as a fellow of the Royal Society of the UK at the age of 32. So he was the youngest living fellow at the time. That's quite an achievement. That put him in pretty good fellowship. So Terence Tao, the Australian mathematician, was also at some stage the youngest fellow, and he was about 32. He wasn't the youngest fellow ever, so Ramanujan, the famous Indian mathematician who loved numbers, could see these amazing number theory formula. He was 31. The youngest ever was some guy who was 21, apparently, who he discovered some kind of variable star, and then he got elected as a fellow of the Royal Society at 21. But he never found out because he died 4 days afterwards of pneumonia. I know. Anyway, so Hawking was, I'm really glad you appreciated that. So Hawking discovered black holes can radiate. And not only did he discover that they can radiate, he was able to write down an exact formula for the temperature of a black hole. And I've reproduced this here because I think it shows how wonderful this was in a sense, how it unifies so many different aspects of physics in one nice formula. So the temperature is T Hawking, T for temperature. And on the right-hand side, we have a whole bunch of, letters and characters. So the first one here is this. This is called h bar, h with a slash through it. It's called Planck's constant. It's a fundamental constant to do with quantum mechanics. And then we have a c cubed. So this is the speed of light again. So that's our tick, that we know that we're also talking about something that has to do probably with relativity or radiation. Down the bottom, well, 8 pi. This is pi 3.14. We've got Newton's gravitational constant in there, so we're doing something with gravity as well. This is the mass of the black hole, m, and this is the Greek letter kappa. It's a fundamental constant of thermodynamics due to Boltzmann. So as a physicist, why I think this formula is so beautiful is it unifies in this one sort of right-hand side here so many different parts of physics. So gravity, thermodynamics, quantum mechanics, and the speed of light, all in one formula, telling me exactly how black holes radiate. So it's a whole bunch of sort of letters here. It's more useful to us maybe to put it into some more familiar units. Let's put it into Kelvin, which is basically the same as Celsius. If you want to go between them, subtract 273. So, and black holes tend to be quite big. So I'm just going to set in units of the mass of the sun. So if your black hole is 1 solar mass, the mass of the black hole over the mass of the sun is 1. If your black hole is twice the mass of the sun, this gives you a factor of 2. So if you have a black hole with about the mass of the sun is pretty heavy. It's about 10 to the power of 30 kilograms. That black hole will be pretty small. It will be about 3 kilometers across. The temperature of this black hole is about 10 to the minus 8 Kelvin. So that's 10 to the minus 8, so 0.000001 minus 273 degrees. It's cold. It has a temperature, but it's not very hot. But eventually, Hawking predicts that this black hole will radiate. As it radiates, it loses mass because it's sort of radiating away its mass in the form of energy. And eventually, it will just go and evaporate. It won't really be, it'll be like Hawking calculated, it'll be more like 1 million nuclear bombs going off. But it will eventually just disappear. And so he was also able to calculate how long the lifetime was of this thing before it disappeared. So this is tau for the lifetime of the black hole, BH. It depends, again, on the mass of the black hole to the power of 3, so cubit. If it's 1, we'll set it equal to the mass of the sun, so this is just 1, times 10 to the power of 74 seconds. That's a very long time, right? So for comparison, the age of the universe, 13 billion years, is about 10 to the 17 seconds. So this black hole, if it exists, a solar mass black hole, it'll hang around longer than we will, and we don't really need to worry about it. If you had a very light black hole, that might just sort of go off in an impressive explosion of radiation, and so people look for those kind of things. So talking about solar mass black holes is not just a fantasy. These things actually exist, right? So these are black holes that we know exist. This is just some sample of them. So by looking at X-rays with X-ray telescopes, we know that these purple guys down here exist. And the LIGO collaboration, as I said before, has seen a number of different colliding black holes, so black hole mergers, within the past few years. Again, these are all around, sort of a few to 30 solar masses. So these solar mass black holes exist in our universe. We can see them that they're there. Not only that they're there, but they crash into each other occasionally. And this calculation Hawking did amazingly lets us know exactly what their temperature is and what their properties are. So this is pretty fab. So he gets the temperature, but he also is able to sort of show what the entropy is. S is used for entropy in terms of the area. So this is A is for area, and these are the constants from the previous page. So this exactly bears out Bekenstein's original idea. So the entropy of the black hole is proportional to its area. So this SBH is entropy. Sometimes the BH stands for black hole. Sometimes it stands for Bekenstein-Hawking. So this is called the Bekenstein-Hawking entropy of a black hole. So we've never measured this Hawking radiation because, as you can see from the previous slide, for the black holes that we kind of know exist, it's extremely cold, right? So we're not really sensitive at all to radiation that is that cold. If you had a smaller one that had exploded, we might see it, but we haven't. So it's not experimentally verified in that sense. And so a sort of an analogy of what's happening here, this is quite a confusing phenomenon. These black holes, which are black and cold in general relativity, when you put quantum in the game, suddenly start radiating. And so the vague picture you have is that quantum mechanics tells you that pairs of particles can sort of be created and then annihilate sometime later. These are called virtual particles. And in the vicinity of a black hole, one of these pairs of virtual particles could pop into existence. One of them might fall behind the event horizon. And then the other one has its pal isn't there anymore to annihilate with and disappear into. And that will sort of fly off, possibly to be detected later on. And that's one of these Hawking particles, which is the Hawking radiation. So this is kind of a microscopic analogy of what's going on in the vicinity of the black hole. It's probably not exactly what's going on. OK. So I've got about 5 or 10 minutes to go. And so this sort of leads into the final. Hawking did 3 really big things I want to tell you about, and I've told you about 2 of them, basically. So the third one is the black hole information paradox. And radiation from black holes, which I just described, this Hawking radiation, led Hawking to consider what is basically his most enduring problem in theoretical physics, and this is called the black hole information paradox. How does it work? Well, quantum mechanics that he was using to calculate this radiation process, it's a theory which does with probabilities. It tells you that you can calculate probabilities for events to occur, and the thing about probabilities is that they should all add up to 100% basically, right? So it's very required for everything in quantum mechanics that when you add all the probabilities together, you get 1 or 100%. And this has to be true for your quantum theory to make any sense. And so a consequence of this is information isn't lost, right? Information is sort of telling you what can occur. You can imagine that I collide 2 particles together. There's some information about those particles, like their mass and their sort of charge and that kind of stuff. And when they collide, that information gets pretty scrambled up, and other particles might be created and come flying out. But if I could perfectly measure everything about these other particles, I could sort of work backwards and reconstruct what was going on initially. Now, in a black hole, the picture is somewhat different. Classical general relativity, gravity, tells you, well, I could send in here 2 sort of spheres of matter. Let's try and make a black hole. We'll get some matter, and we'll just fire it at each other. So there's information contained in that about what the matter is and how it's arranged. And if we fire it at each other hard enough, we'll make a black hole. And then that matter will disappear behind the event horizon. The information goes behind the event horizon, and I can never know what it is again because it can never come out from behind the event horizon. So the information disappears behind the horizon here. So Hawking showed that black holes radiate and eventually evaporate. And he was also able to say about the form of this radiation that it's basically random. There's no information about what happened earlier goes into this radiation that comes out of your black hole. So going in, you have a bunch of matter perhaps, and there's information in that matter. And then if you wait a time later, you get this black hole radiation coming out, but it's completely random and it has no information in it anymore. So where's the information gone? This would appear to violate a fundamental tenet of quantum mechanics. So you could say, well, OK, fine, the information just disappears and the radiation is random. This would violate quantum theory, which we know and love as physicists, and is one of our best tested theories. Well, OK, maybe there's 2 copies of the information. one sort of stays inside the black hole and the other one flies out somehow. Well, it turns out you can't clone information in quantum theory. This would also violate quantum theory. Maybe we just need to change quantum theory then. This is Hawking's initial position, and he sort of went back on this later on. Or it's possible that we'll only sort of know how this works when we have a consistent quantum theory of gravity, right? This is why this information paradox is so strong and sharp. It takes two of the best theories we have, general relativity as a theory of gravity, quantum mechanics as a theory of small stuff and radiation, and says, look, we can put them together and do this calculation, which looks pretty reasonable, and then, by the way, now quantum theory is probably wrong, or you have to change general relativity. This has wrecked people's heads for 40 years. And so it's possible that the only way to answer this is when we have a theory, a proper theory, which is a quantum theory of gravity. I told you earlier on that even Hawking in his book was saying, we don't know what's happening at that singularity, right? When that singularity in the black hole exists, we have infinite force and big space-time curvature. You need to have a new theory to describe that, and it's possible that this calculation is telling us that new theory is really required to understand what's going on here and pointing the way towards it. So gravity is a tricky one from the perspective of quantum theory. We kind of knew that, people knew that a bit already in the 60s, but this really brought it into focus. So we know that there's about four forces, four is an exact number, in the universe. So one is electromagnetism, describes electric and magnetic phenomena. One is called the weak nuclear force. It gets you stuff like radioactive decays. And one is called a strong nuclear force, and it's sort of responsible for things like binding nuclei together. And these are very well understood. We have a theory, a physical theory called the Standard Model, which sort of sticks them all together, and it's our best tested theory that we have, and it works extremely well. And they're consistent with quantum theory. You can do all of this stuff at the quantum level. And then on the other hand, in the naughty corner, we have gravity. Right, so reconciling quantum theory with general relativity is one of the major aims of contemporary theoretical physics, and which occupied Hawking and many, many other people for quite some time. So do we have any ideas of what this sort of quantum theory of general relativity might look like, this quantum theory of gravity, which we probably need to understand this black hole problem? Well, the best sort of known, and in some sense the front runner, is a theory called string theory. So string theory sort of says, well, normally when we're talking about fundamental physics, we think of things being made out of particles, like electrons, and there's smaller stuff inside protons. Protons are particles, but there's smaller things inside protons. Neutrinos. The neutrinos are on the front page of the Age today. Fantastic. String theory says, well, they're not particles. If you looked a bit better, and much, much better, you see that they're actually things like strings. They could be closed strings like this, or they could be open strings. And you can work out, with some difficulty, the mathematics of that and what that implies. And it turns out that string theory, if you go from particles to strings, is a theory of quantum gravity. And what we don't know is it the theory. So string theory has some nice things going for it. It definitely, like, even if you just say theory contains strings and do some maths, it turns out you get general relativity for free, basically, which is pretty great. We know it contains interactions that look like these electromagnetic and weak and strong interactions. That's not obvious from talking about strings in general, that's good. And there's stuff you can calculate in there. So in the 1990s, two physicists at Harvard were able to sort of write down in string theory equations for a black hole. And they were basically able to do this counting game with entropy. So previously we'd sort of said we can count toys in a tile. These guys in string theory are able to count up all of the different little configurations of the black hole and get exactly the same answer as Hawking had done back in 1975 from within string theory. So this was sort of viewed as quite a good victory for string theory. On the other hand, there's an awful lot of stuff that we can't calculate in string theory and that we don't understand very well about it. Also, it requires 10 space-time dimensions, which does not seem to gel very well with our everyday experience. So lots of people don't like it for that reason, which is kind of fair enough. I mean, there's ideas that you can take the other 6 dimensions and you can curl them up really small, and then ta-da, look, there's 4 left. But this is a bit of a bother, right? It's still unclear, even though it's a theory of quantum gravity, how exactly the information paradox, where this information from the black hole goes, gets solved by string theory. And it's also unclear how to get this standard model that we know describes our universe out of string theory. So people have been working on it for quite some time now. But it's obviously a mixed bag of success in a sense. You know, we understand it a bit better. It can do some cool stuff. And there's lots of stuff we don't understand about it. And maybe it's just a theory of quantum gravity and it's not the right one. Maybe there's multiple theories of quantum gravity. There's a few other ideas that people have, but they are even sort of less well understood than string theory, which is why I've gone with this one. So that's where Hawking sort of left us in that. So I don't want to give, and this sort of is about 1977, right, when this happens. So I don't want to give the idea that sort of Hawking's career was do awesome stuff in 1970 to 1977, and then it's kind of like done and dusted, and then he was twiddling his thumbs for the next sort of 40 years. That's not true at all. I've told you about these three things. These are kind of the biggies in a sense. So the singularity theorems, you know, saying that we need to take black holes seriously, saying that black hole thermodynamics happens and predicting the existence of Hawking radiation, and then setting us up with this big problem, the information paradox. But if you went through his later career, you can find a whole lot of, like, this is just stuff that's named after him, right? He wrote like 180 papers, and these are just the ones that ended up with something named after him. Hawking energy, Gibbons Hawking ansatz, Gibbons Hawking space. So Gibbons was a student of his who was very good and ended up being a professor at Cambridge. Chronology protection conjecture, which sounds awesome. Gravitational instantons, so many different things he contributed to through his career, you know, which aren't these ones. And basically any one of these, like these ones for sure, and even these ones, if you did any one of these, you would be very happy with yourself as a theoretical physicist. So where does this sort of leave us? Well, the information paradox is an enduring problem of theoretical physics for the past 40 years, basically, right? It's about 1976, 77, he posits it, and we still don't know what the answer is. Lots of solutions have been proposed. So in string theory, sometimes people talk about fuzzballs, where a black hole doesn't exist. Instead, if you looked close enough at the black hole, it's this kind of weird fuzzy state of a bunch of strings. Some people like that, some people don't. I don't really know much about it. Hawking's original one was change quantum mechanics. It's known that there's problems if you want to do that, sort of in a naive sense. Another idea, Hawking's most recent one, he wrote a paper in 2015 about this, was that information is somehow encoded in very low energy radiation which escapes the black hole, which is an interesting idea, but again, not widely accepted. Another idea is called complementarity. So the information inside the black hole is somehow, there's lots of somehows here, encoded on the event horizon, and that would, you know, solve the information problem somehow. So an issue here is that we don't know the theory of quantum gravity, right? So it might be that we just have to know the right theory in order to actually go and calculate this instead of doing partial calculations and that kind of thing. But whatever the solution to the information paradox is, I think it's sort of guaranteed, like when you look at the solutions people are proposing, to really alter our conception of space and time, right, in a really fundamental way. And Hawking didn't get to solve this, right? And I don't think that's a sad thing. I think that he left this one behind for us to solve is pretty awesome. Fermat didn't solve Fermat's last theorem. He left it, and it took 200 years of progress before Wiles solved that one. Riemann didn't solve the Riemann hypothesis. And Poincaré did not prove the Poincaré conjecture. That took a century as well. So I think leaving this one, you know, being able to take the field from a situation where people didn't even know if black holes existed or singularities, show that they did, show thermodynamics, and then leave us with this massive problem in theoretical physics, one of the greatest that's out there. Leaving that actually as a question for us to solve in the future is, I think, in some sense, his greatest legacy. It's a sharp problem, and he's thrown down the gauntlet to everyone. You do not understand what you're doing in quantum gravity until you understand this problem. Okay? Thanks very much.
Thanks, Matt, for a really interesting talk on the life and contributions of Stephen Hawking. Got time for some questions from the audience. Yes, got one down the front here.
There's something I probably should know that with regarding the inability of light to escape from a black hole in the context of gravity. Now, with gravity, there are particles with masses, and light, electromagnetic radiation, the smallest quantum of electromagnetic radiation is the photon,
Yep.
which has zero
Yep.
mass. Now, how can something, and of course you can't find a photon that has zero less mass, it's got to be travelling at some speed, as I understand it. So how does gravity affect something with zero mass? And also, in regard to the Hawking radiation, and I accept it, it does happen, I know,
Aren't we all?
The Hawking radiation, that's produced by something like a photon in the quantum vacuum. A positron and an electron spontaneously appear.
As an example, yep.
The positron or the electron disappearing into the black hole, and the other thing is ending off somewhere. At least those things have got some mass, albeit.
So you don't actually have to have mass for this stuff.
Maybe not all of it.
Yeah. So the question is that gravity is sort of to do naively. Sorry, I don't mean your question is naive. Your question is very good. Gravity, we think of gravity usually has things to do with mass, right? Things that have masses are affected by gravity. But we know from quantum theory, as this gentleman said, that photons do not have a mass. So photons are the quantum particles of light, basically. So given these two facts, how does sort of the black hole radiation work? So the resolution is that even though photons don't have a mass, they do have energy. So the fact that they're moving, as you say, they don't, you can never have a photon at rest. It moves, so it has some momentum through moving, and that momentum gives it an energy. Once it has an energy, in the Einstein equations, which I put up before, then gravity sees it. Anything that has an energy, gravity basically sees an effect and can affect. Yeah, but you can have E equals mc squared, but there's a slightly more general one as well, such that even if you have zero mass, you still have an energy. And so that can sort of resolve this. Gravity will still see the photons, and so if you have zero mass photons, as you were saying, they can still undergo this Hawking radiation and fly out from the black hole.
Another question? Gentleman here had his
Sorry? Good. So the question is, with the Large Hadron Collider at CERN, can that take us anywhere towards answering this question? So the Large Hadron Collider is this big 30-kilometer collider, particle collider, which is currently operating underneath, near Geneva, not actually underneath Geneva. It operates at very high energies from what we're usually used to. Can it help us with this? My feeling is probably not. Sadly, it's perhaps possible, but I think probably not. I think the energies that you'd have to go to really sort of see these quantum gravity effects are far above what the Hadron Collider can achieve, I'm afraid. There are some theories that say it might be possible, that these effects might be important and should be visible in some sense. But I think the consensus opinion would be that it's not going to help us that much with it, I'm afraid.
I think we've got time for one more question. This gentleman in the back.
Yeah, just wondering, how big is a black hole being in thermal equilibrium with the universe? Is what it says in Dolan.
Oh.
Does that have any implications for
That's a very good question. So, yes, Stuart. So the question is, if I had a black hole, which was so the universe is filled with a kind of background radiation. This is called the cosmic microwave background, and that radiation has a temperature, and it's about 3 Kelvin, so about minus 270 Celsius. So the question is, black holes also have a temperature, and if we had a black hole that had the same temperature as this background radiation, does that imply anything important for astrophysics? Off the top of my head, I couldn't tell you what the mass of such a black hole would be. It would be less than the solar mass. So that's right. It would be sort of less than the mass of the sun. It would have a reasonably long lifetime, so they'd still be hanging around if they were created early in the universe. And since they're in equilibrium, they wouldn't be doing an awful lot. They'd be sort of emitting some radiation, but they'd be absorbing some as well. However, as the universe gets older, it cools down, right? As this stuff spreads out, it becomes colder. And then your black hole is going to be warmer than the background radiation. And then it's going to start emitting all of its Hawking radiation. And as black holes emit radiation, they get hotter. They don't cool down by emitting radiation. They get hotter. And once it's out of thermal equilibrium, it'll emit radiation, and then it will just sort of go on this, its death spiral, basically, and eventually radiate itself out of existence. So the short answer to your question is I think they don't, at the moment, have any really important astrophysical implications for us. The ones that do are the really light ones. So the really light ones are the ones more likely to be sort of evaporating around now, and they're the ones that we might sort of see if we are lucky and have a telescope pointing in the right direction at the right time.
Okay, I think we're out of time this evening. I'd like to thank you all for coming. And before we thank Matthew again for a very enjoyable lecture, I'd just like to remind people of the next two Fridays in July. We'll have the final two lectures in our 2018 July Institute of Physics. So please join me in thanking